Hello everyone, welcome to the course on computer-aided drug design. We will continue on the topic of QSAR because QSAR is very important, which gives you the structure activity relationship mainly between the descriptors or structural features and the activity. I showed you this in the previous class. So you have certain molecules, okay, whose activities are known and their minimum energy conformations are known. So we use different softwares. I showed you different softwares where we can calculate descriptors. I will show you some more softwares later. Now you have large number of descriptors, okay, so you can shortlist descriptors based on the correlation coefficient between the descriptor, a particular descriptor, and the activity, okay. And please remember, if you have 5 data points, you can think of having only one descriptor model, okay. So if you have 5 data points, you should not go beyond one descriptor model. If you have 10, then we can have 2 descriptors or 2 independent variables, that is x1 and x2. Then those descriptors should not be cross correlated. That's very important, because some descriptors like molecular weight and size of the molecule may be related to each other, so they should not be cross correlated. They should be very dissimilar between each other, okay. So we can do different approaches so that you select the best descriptors which are far apart, not correlated, and so on. This is valid only when you are talking about more than one x, okay. If you are thinking of only one x, then these things don't matter. Once we do that, we develop a regression relationship, okay. We estimate a lot of statistics. These are statistics we will talk about in the course of next 1 or 2 lectures, and then see how good the fit is, okay. So you develop a regression relation, but parallelly you divide the data set into training set and test set, okay. So if you have, say, 10 data points, you don't take all the 10 data points and develop the regression model. Around 20% of the data you call it test set, you keep 80% of the data for the training, and then you develop the regression relation using that 80% data, okay. Then once you have a good model, you try to predict for those 20% data which you had kept aside and see how good the fit is, okay. That's why you divide the data into training and test set. 80% of the data in training, 20% in the test set. That's how you need to do. Remember that. Even if you have 6 or 7 data points, take 5 data points for your training and keep the other 2 for test. Once you develop a regression model, and then once you are happy with all these, try to predict those 2 data points which you had kept aside, the activity of those 2 data points, and see how good the prediction is, because ultimately QSAR is meant for predicting activity of unknown new molecule, okay. That's very important. Once you have done it, you are very happy, you have a QSAR. You can use this relationship for predicting new molecules, activity of new molecules, and so on. Actually, this is how the workflow happens. So the main challenge is to reduce the number of descriptors and take those descriptors which are very good, which you think are very good. Like I showed you yesterday, a software called Dragon which predicts almost 2000 descriptors, and you don't know which one to select, which one is the best for you, okay. That's very important. So that is why that's a challenge in QSAR. Sometimes we may end up selecting the wrong descriptors or descriptor, we may miss out the important ones. So those things are there. So descriptors: topological, electronic, thermodynamics, structural, 0-dimensional, 1-dimensional, 2-dimensional, 3-dimensional properties, and so on, actually, okay. So the QSAR, the main challenge is shortlisting the descriptors. That's very important. And also, as I said, we need to have some experimental data activity for some molecules. So we can go to literature and try to collect activity. So before I start synthesizing new molecules, I may go and look into the literature and see whether activities have been reported for molecules of similar structural features, and then collect them and develop your QSAR and then proceed further. Okay, so what is the main use of this regression? QSAR is nothing but regression, determining which factors are important in a system, okay, building equations that can be used to predict behavior for new molecules, new operating points or new conditions, okay. That's the advantage. So I can use QSAR, QSTR, QSPR, either for property or toxicity and so on. Okay, so initially we may need to have data from literature or from lab assays, and then develop the regression model. So like I said, we must have at least 5 data points for one parameter model or one descriptor model. Perform the regression, see whether the fit is good, determine the statistics like R square adjusted. We will talk about what the definitions of all these. The rule of thumb is 20% of the data for validation or test, 80% for your training or fitting the data. That's very important. So you could have, you can select the X which seems to have good correlation with Y. Y is your activity, X is your descriptor. So if there is no correlation between Y and X, that is Y axis is Y, X axis is X, that is activity and descriptor on the X axis. If they are not correlated, it may look like this: slight correlation, reasonably good correlation, very good correlation. Okay, so as X descriptor value increases, activity also increases. You can also have a negative very good correlation like this. So as the descriptor value increases, activity may be going down. For example, lipophilic systems may not work on hydrophilic assays. Okay, so as the lipophilicity increases or log P increases, the activity may be going down. So you can have both negative as well as positive value. This is the ultimate, the best. Okay, but you can have in between like this actually. Okay, so you can find out whether initially the correlation coefficient between a descriptor and the activity falling between -1 to +1 and larger, closer towards these 1 or -1, you can say it's fantastic. Even 0.5 above 0.6 is also good. So we can select the descriptors which appear to have good correlation coefficient. Okay, so we can start with a simple linear regression. Okay, so we can have, say, activity on this side, one constant plus B1 into X. Like I showed you one example yesterday, X could be your molecular volume or dipole moment. Okay, so it could be molecular weight and so on actually. Okay, or log P. You can also have single parameter squared, log P square, log P cube. Generally we will not have cube and all, but we can have square in certain situations. Of course, remember, you may need to have more data points so that we have enough degrees of freedom if you want to have square type of model, because there are 3 unknowns here. We can also have 2 parameter model. We can have log P and say electrostatic, okay, sigma coming here. So again, as you can see, the more number of parameters, more complicated, the quadratic, you have so many unknowns. Okay, so you need to have a lot of data points so that the degrees of freedom is satisfied. So basically a little bit of statistics. So you are trying to minimize the sum of squares. So Y is the activity as measured, that is experimental. Y model is the prediction of the regression. So this is squared, you are taking sum and then you are trying to reduce this. This is what it is all about actually. You are trying to minimize the sum of squares of this. Is called error or residual, because this is measured activity and this is as predicted by the model. So this should be as low as possible. You are squaring it so that minus or plus, it will always be positive, and then you are taking a summation. Okay, this is sum of squares of the error or residual, that is called. Okay, so there are a lot of softwares which can do that. So when you are doing a one parameter model or one descriptor model, you have Y. I put hat because it's called prediction. Normally we put a hat. Y is equal to Ax plus B. X is your descriptor, log P or molecular volume or molecular weight or dipole moment, whatever it is. So you are trying to get a least square line fit. This is called as least square because you are trying to minimize the square here, right? That is why it is called least square. So if your model is Ax plus B, then you are trying to minimize. Y(I) is the prediction, Ax plus B is the model. So sum of, you are squaring it up, difference, you are squaring it up, taking a summation, you are trying to minimize this. Okay, this is what you are doing. So if you want to minimize a function, what do? We take a differential with respect to A, equate it to 0, then take a differential with respect to B, equate it to 0, and then you have two equations, two unknowns, you will calculate for A and B. That's what you do if you remember minimization in your calculus. Similarly, you can have a square, okay? Y is equal to ax square plus bx plus c. So x could be log p, so you could be having log p square and log p here. So we have three parameters. Again, you are trying to minimize. Yi is your actual experimental data. This is your prediction. Okay, so difference, squaring it up, summation, you are trying to minimize this. So if you want to minimize this, what do? We take a differential with respect to A equated to 0, differential with respect to B equated to 0, differential with respect to C equated to 0, then you estimate A, B, C, because we have three equations, three unknowns. Okay, basically this is how it may look like. Okay, so for example, if I have yesterday in the previous class also I showed you how to calculate. If it's so simple, it's very easy to do. Okay, using Excel, we don't have to sweat it out at all. Okay, so we do this. So this is log p, for example. We call it log p 1, 2, 3. Say we say activity, then 0.5, 1.5. Okay, so this is very simple. We can use the graph here. Okay, so we got it here, right? That's what is shown here. So we can get the regression relationship, add a trend line, then we can say display equation r divided r square. As you can see, the slope is 0, it passes right through the origin, and y activity is equal to 0.5x, r square is 1. I have given a very simple looking data, so that's why r square comes to be 1, but in real life r square may be 0.7, 0.8 and 0.9. it will never become 1 actually. Okay, so simple. If you have a single descriptor model, anybody can do it using Excel. There are many softwares also for us to do. Okay, so y is equal to mx plus c, that's the equation you are trying to solve. So the two equations, if I use calculus like I mentioned, for minimization we get summation of y is equal to m into summation of x plus n into c. N is the number of data points, here it will be 3. Other equation will be summation of xy is equal to m into summation of x square plus c summation of x. Basically you are taking this equation, doing a summation all over, and then you are multiplying by x, again taking summation. So you have two equations here, two unknowns m and c, so we can calculate. So what do? X is equal to 1, 2, 3, y is 0.5, 1.5. So we need x square, right? So x square is 1 into 1, 1, 2 into 2, 4, 3 into 3, 9 here. We need this here, xy. Xy is equal to 1 into 0.5 is 0.5, 2 into 1 is 2, 3 into 1.5 is 4.5. So we are trying to summation. Summation of x is equal to 1 plus 2 plus 3, that is 6. Summation of y is equal to 3. Summation of x square is 14. Summation of xy is equal to 7. So now we can substitute here. So this will become 3 is equal to m into 6 plus 3 into c, and this is 7 is equal to m into 14 plus c into 6. So we will have two equations. Okay, that's what it is. We'll have two equations for m and c. We can solve this. Okay, so what do you get? We get m is equal to 0.5 and c is equal to 0. In fact, that's what we got in our Excel also, right? That's what we got in our Excel also. Okay, m is equal to 0.5, c is equal to 0. So this is the principle by which this particular thing works. Okay, so the if you do not have Excel, you can do it. This is the basic by which it works. actually. So summation of y is equal to m into summation of x plus nc. Summation of xy is equal to m into summation of x square plus c summation of x. Basically you are taking this and getting this equation, and you are multiplying by x, and then you are getting this equation. So summation of x is nothing but adding up all the x values. Summation of y is adding up all the y values. Summation of x square is nothing but calculate x square, and then adding all of them. Summation of xy is equal to x into y, and then adding all this. So you develop two equations, two unknowns m and c. You can solve it, and you end up with c is equal to 0, m is equal to 0.5, and that's what you got in your Excel also, correct? That's what you got in your Excel also. Okay, that's what you got in your Excel also. So this is the principle by which you get the m and c. So if you have one parameter, it's very simple. With Excel you can draw the graph and then calculate the regression equation and r square. If you do not have Excel, you can use this formula to calculate the m and c. Okay, this is the principle by which it works. Okay, so what happens if you have two variables? That means two descriptors, x1 and x2. So you have m1, m2, two slopes, and c. So you have three parameters. So basically you need three equations. So how do you get the three equations? This is the first equation. Summation of y is equal to m1 summation of x1 plus m2 summation of x2 plus nc. The other one will be multiply by x1. That is, you get this equation, x1y is equal to m1 x1 square plus m2 summation of x1 x2 plus c summation of x1, and then multiply with x2. So you get summation of x2y is equal to m1 summation of x1 x2 plus m2 summation of x2 square plus c x2. So you see you have now three equations and three unknowns, m1, m2 and c. So we can solve this and get these three constants. So then your QSAR will be this. This is a two descriptor problem. Okay, so descriptor 1 could be log p, and descriptor 2 could be sigma, or some electrostatic parameter here. Okay, this is your QSAR equation. Of course, when you have this type of model, when compared to one descriptor model, you should have at least 10 data points. So as per rule of thumb, 5 data points, you should stick to only one descriptor model. Approximately 10 data points, you can go for two descriptor model. Okay, at least 8 data points you should have. Of course, that's not correct, because if you want to divide the data into training and test set, so even if you have 7 data points, 2 of the data points you can put it as test set. So 5 data points you can develop a single model. So if you have 10 data points, so 2 of them you can keep it for test set. So with 8 data points we can maybe develop a 2 descriptor model, and then try to predict for the other 2 data points the activity value. So this is how it's very close. So ideally you should go to 10, 11, 12 like that, so that we can have a 2 descriptor model. Remember that we should have enough data points so that we have enough number of data points in the test set as well as the training set. So what are the steps in regression which I showed you? Specify the form of the regression model, linear or quadratic, x1 to xj, which one to include. So they should not be cross correlated. That's very, very important. Okay, perform the regression analysis using training set data, compute so many parameters, mean, variance, r squares, r square adjusted, r square predicted, q square. We are going to do that. Compare the predicted versus actual values, how well the regression fits. Check the residuals. Residuals is that error, y experiment minus y predicted, that's called residuals, and see how they look like. Okay, identify the important ones. There may be some descriptors which may not be very important, and then we can remove those. Okay, we can take only those which are important, and then again fit the data. Like that we can do actually. Remove insignificant terms. Okay, then look at the final regression model. This is how go about. So these diagnostic statistics, that is r square adjusted, r square predicted, Sometimes some people use Q square, so many things. Look at residual plots, then run the test data. These three are very important when you develop a QSAR. Don't think QSAR is just a mathematical fit using a software and that's it. It's not correct. You must look at these p-values, R square adjusted, R square predicted, Q square and so on. Look at the residuals. See whether there is some pattern, there is some problem in the residuals. Then run the test set or validation set and see whether the model is able to predict that data. Then only you can say your QSAR is good. Until then, you cannot trust the QSAR. Please remember, QSAR is not fitting some points using a regression line or a quadratic model, and then that's it. You need to spend some time, think, and see whether there are some hidden mistakes. Okay, I'm going to show many of them where you can goof up. Now let's look at these statistics. We call it goodness of fit. R we know is the correlation coefficient. There is something called R square. Is the fraction of the total variance that is expected by the regression equation. So y minus yi hat, yi is your actual experimental, y hat, as I said before, is your model prediction, and yi minus y, that is why this y is the average of all the y's. This is the average of all the y's. Ya minus y, this is called total variance. This is sum of squares of the residuals. This is residual because this is experimental. This is what the model predicts. So this difference is called the residual. This is square sum. So it's sum of squares of the residuals. Yi minus y, this y, as I said, is the average of all the y's. This is called total variance. This is called R square. R square generally should lie between 0 to 1. It will not go to negative because it's a square. And 0 means very, very absolutely no relationship or fit. 1 is best. So when we are doing experimental in the labs with drug discovery and all that, we may have R square maybe 0.7, 0.8. We can say it's very good, reasonably good. But when you are doing some simulations, modeling, then you may get very high R square. But experimental, you will get only this R square. So this is 1 minus sum of squares of the residuals. That means this is the experimental, this is the model prediction. This could be say mx plus c, like, or m1 x1 plus m2 x2 plus c. It predicts. So this different square. This is yi experimental minus y. This is the average of all the y's. This is called total variance. This is called R square. Degrees of freedom is the number of model parameters minus 1. The rule of thumb, the number of points should be at least 25% more than the number of degrees of freedom in the regression equation. So if you have y equal to mx plus c, that is one parameter model m and c or 2, so 25% more, so you should have at least 3 data points, but we always say we should have 5 data points. We are trying to be more careful. So 3 data points, yes, you can fit a model, but you will not be able to have a test value there, right? So if you have a 5, 6 is good, because then one of the points we can use it for test and the remaining 5 we can use it for model fitting. This is the rule of thumb. There is something called R square adjusted. So R square adjusted is nothing but 1 minus sum of squares of the error divided by sum of squares of the total. That is this one. This is sum of squares of the total variance. N minus 1 divided by n minus p. N is the number of data points, p is the number of terms in the regression model. That means y is equal to mx plus c means we have p will become 2. So we can write it as 1 minus n minus 1 divided by n minus p into 1 minus R square. So R square adjusted will always be less than R square, and if you have more number of parameters, terms in the regression model, R square adjusted will come down because you have negative here and here. Okay, so we can, with more parameters, we'll be able to fit the model. R square will become good, but R square adjusted will become bad. Okay, so more number of parameters, R square adjusted will come down. So the challenge is to keep less number of parameters but still fit your model. That is the greatest challenge for you. So R square adjusted will always be less than R square. Then there is something called predicted R square. Sometimes we use R square predicted, some people use Q square, capital Q square. This is called cross validated R square. Okay, this is slightly difficult to understand, but let me see. Suppose we have so many data points. When we fit the equation, we get R square. But what we do is, for predicting this R square predicted or Q square, we remove one data point, fit with the -1 set of data. That means if you have n data points, we use n-1 data point, fit the equation, fit the model, and then try to predict the value for that point which was missed out. That is, evaluate the error at the removed point. Okay, so then square it. Now you remove another point, keep this point but remove another point, again develop a regression model, then try to predict the y value for that point, and then get the residual, square it. Like that we keep on adding all the sum of squares of the errors or residuals. Okay, that is called predicted sum of squares or PRESS. It is also known as LOO, leave one out method, because every time we remove one data point and then try to develop a model, try to predict the value for the number which we have left out. Once we get the PRESS, what do? We do 1 minus PRESS divided by sum of squares of the total. That will give you R square predicted or Q square. Okay, so if you leave out one point at a time, that's called leave one out method, 1 point at a time. Do you understand this? So suppose there are n points, we leave 1 point out, so we have n-1 point. We develop a regression model with that n-1 point, then try to predict for the nth point which we have missed out, find out the residual or error, square it. Then you leave another point, keep the previously left out point, so again you will have another n-1 points. You develop a regression model, predict the value for the point which was left out, get the error, square it. Like that you repeat for all the n points, add up all these square of the errors. That is called PRESS, predicted sum of squares. Then 1 minus PRESS by sum of squares of the total will give you R square predicted or Q square. Okay, it is cross validated R square. People use different terminologies here. Instead of 1 point, we can also leave many points. We can also do leave many out method. Just like leave one out method, we can also have leave many out method. That means instead of 1 point, we can miss out 2 points and develop a regression relationship, and then try to predict the data for those 2 points and repeat the process and get errors. So this is a very stringent R square. So that is why Q square will always be lesser than R square adjusted, which will be lesser than R square. Okay, so these are different R squares. Now more, there is something called bootstrap R square. This is the average of squared correlation coefficients calculated during the validation process. It is computed from the subset of variables used one at a time for the validation process. So I can leave 1 point at a time, okay, and then do it for the validation. I can take, suppose I have 7 points, I may take 2 points as a test set, remaining 5 points, and then develop a R square model. Then I can remove 2 points, some other 2 points, and then again develop R square model. Like that I took many R squares I'll get, right? So I take the average, then that is called bootstrap R square. Okay, then there is also called R square M test. Okay, this R0 square is the squared correlation coefficient between the observed and predicted values of the test set compounds with the intercept set to 0. So I also mentioned that we should have some test set, right, apart from training set. So with the test set, what you do is we do a R square M test using this particular formula, where R square 0 is squared correlation coefficient between the observed and predicted values of the test set compound with the intercept set to 0. That means you force the intercept to pass through the 0 and get an R naught square. Without allowing it to pass through 0, you will get an R square, and then use this formula. That is called R square M test. This is more stringent. Okay, so you are forcing the line to pass through the 0 to get this R square. Here you are not forcing it, so you get this, and then see whether the value greater than 0.5, so that the model can be accepted. Okay, then we also have other approaches, R0 and R0 dash. These are corresponding correlation coefficients for the regression through the origin, where we have I observed is equal to K YI predicted, or YI predicted is equal to K dash YI observed. Okay, so we see we fit a model this way, we fit a model this way. Okay, so this becomes here, this becomes here, and then you allow it to pass through the origin, and then okay, get the R0 and R0 dash. Okay, then you see whether those are quite good, above 0.6. Okay, so these are different ways of testing it out, whether your model has good predictive capability and whether your model has good fitting capability. Struture and co-workers also suggested some more approaches for predicting and validation criteria. They said Q square should be greater than 0.5, R square should be greater than 0.6, R square minus R0 square by R square. Okay, should be less than 0.1, and the K here should be between 0.85 and 0.15. That means it should be close to 1. Similarly, the K dash also should be quite high. Okay, so many different things they mentioned. Okay, here basically, so many things. So they said R0, as I said, R0 square is when you calculate the R square when you force it to pass through the origin. Here you have R dash square when you force it to pass through origin. R dash involves you develop a model between predicted and observed, whereas here you observed versus predicted, we are developing a model. Okay, so in both the times this K and K dash should be very close to 1, that is 0.85 to 1.15. So there are so many different criteria we need to follow to ensure, to ascertain that we have good fit as well as good predictive capability, and we are not trying to overfit our data. That's very, very important. Not overfitting our data. That's very important. So these are the various parameters which we are talking about. Okay, we have R square, we have adjusted R square, we have Q square or cross-validated R square, bootstrap R square, R square M, R0 square, then we have K dash, R dash not square, and so on actually. Okay. Another important point is to see how good the fit is based on the test set data also. We will continue more in the next class. Okay. Thank you very much for your time.